Hi everybody, it's Mrs. Mancuso with some AP Bio review for you. One of the topics that someone asked about is going over the nervous system. So your nervous system is how you respond to stimuli. And you need to respond to so many stimuli during the day. It's amazing. Some of it is external, like somebody's laughing and you're like, wow, what are they laughing at? What's going on? Or sometimes it's an internal stimuli, like you're hungry and your stomach starts making gastric juices and it starts growling. So there's a lot of stimuli that you have to respond to, and your nerves do the job of your nervous system. So your nervous system is broken up into different sections. So first of all, you have a central nervous system. That's your brain and your spinal cord. And you have your peripheral nervous system, peripheral. All right, and those are all the ones that extend out from your brain and your spinal cord. Some of them are autonomic. That means they're automatic. They work without thinking about it. And some are somatic. Somatic goes to your muscles or your fingers so that you can like move this on purpose because I'm thinking about it. Your autonomic are divided into two sections. They are your sympathetic and your parasympathetic. Your sympathetic works to speed up your heart rate and speed up your breathing. So this is what I like to call your fight or flight response. Well, not I like to call it, that's what it's called. So when you are speeding up your heart and your breathing and all that stuff, you're decreasing digestion. You're putting the focus on increasing your blood sugar levels and getting your muscles ready to go do something. Parasympathetic is rest and digest. So this is going to increase digestion because you're just in chill mode. You can lower your breathing rate, lower your heart rate, and just chill. So when you're not like responding to something, your parasympathetic nerves are active. All right, let's talk about nerves. Nerves have a very specific shape and they have a specific sequence. So here is, let's say your finger. So your finger has dendrites that extend out. That would be the cell body. I know I am literally awful at drawing. But there's one nerve, and this nerve is my sensory neuron. So these dendrites can extend into your skin or from your eye or your taste buds or anything like that. So they're picking up the messages. On the dendrites are receptors, and so they're able to receive messages. Impulses only go in one direction, and impulses are all or nothing. So they either send, it's either full send or nothing. And then from a sensory neuron, the next neuron is going to be an interneuron. And so an interneuron is what you have in your brain or your spinal cord. And then the last one is going to be a motor neuron. So this is the most basic pathway, is to have these three things. A motor neuron ends with a muscle or a gland. We call that an effector. Effector. I don't know why I'm putting a Y on that. Effector. So your effector is what's going to receive the final response. If you do this pathway, you have done a reflex. So like I touch a hot stove, I pull my hand away. That's because the message went from a sensory neuron to my spine and then back to the muscles in my finger to pull it out of the way. So this is a basic reflex arc. Okay, now I want to show what's happening in the actual nerve. All right, so here were my dendrites. Here's my cell body. Here's the axon, and here's my axon terminals, and this is my synapse. Okay, inside of the neuron, there is a polarized condition. So at rest, this is polarized because there is a difference in charge. It's pretty much around negative 70 millivolts inside an at-rest neuron. The difference in charge is due to the fact that you got a lot of negative DNA inside, and there's a difference in the ions. There are more Na plus outside, and there are more K plus inside. So in order to send an impulse through, there has to be a change in polarization. So we always do this graph. So we start off at negative 70. This is the membrane potential. So that means what's the charge inside. So it starts off at negative 70. If you receive a ligand, it causes gates to open, 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 open. And the first gates that open, if it is excitatory, the first gates to open are sodium gates. And sodium comes in. So if I have negative 70 in here and I'm adding a positive, this is going to go up. So right here, Na plus gates open. And Na plus is going in. And it is depolarization. As long as I meet a minimum level, this is called my threshold. So let's say this is negative 55. As long as I meet the negative 55, I'm going to open all the gates. Open, 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 open. Lots of sodium comes rushing in. Well, potassium responds, and potassium gates open. And they can be on either side. And now potassium starts going out. Well, sodium closes, potassium opens. So right here, I do a downswing. That means my Na plus closes and my K plus opens, and K plus is going out, which means my charge is going to go back down. And when it actually responds, it goes too far. So this is called hyperpolarization. I might have gone to negative 80. That's because potassium gates close slower than sodium gates, so the response wasn't as quick. And then the last thing, I have to go back, and this part right here is called my refractory period. My refractory period is, okay, these are on the wrong sides. I am going to have to pump Na out, and I am going to have to pump K plus in. This pump only works by active transport because I'm trying to move sodium from a low to a high. That's against the gradient. And I'm trying to move potassium from a low to a high. That's against the gradient. So the sodium-potassium pump is what's active right here to get everything back to rest. And I need it back at rest to send another impulse. Well, if you think about it, I haven't really sent any message yet. So at the end of this, there's calcium gates. And when a calcium gate opens, calcium comes in, and there are vesicles here. Inside the vesicles are neurotransmitters. Those neurotransmitters and vesicles get pushed to the edge, and the neurotransmitters get released. Those neurotransmitters will be picked up by receptors on the next neuron's dendrites. So here's my next neuron. There's the axon, there's the dendrites, and I'm picking up the message. So nerve impulses are both chemical and electrical in nature. It doesn't really show the calcium part here because this is truly looking at the electrical part of it. You have to look at the neurotransmitter release to see the chemical part of it. And if I talk about medicines for a minute, medicines can block receptors. And so if you have a medicine that you're taking, a pain blocker, let's say you had ACL surgery. Well, you don't want to feel that amount of pain in your knee. So you actually have pain blockers. And pain blockers will block these receptors so that the neurotransmitters aren't sending the message, because the message is like, it hurts, it hurts, it hurts, it hurts. I get it. It hurts. You don't want to feel that constantly. So pain blockers block the receptors from receiving the pain message again. All right. Thanks for joining me.